Now we're in section 6.4, talking about another application of integration that we're just going to touch on a little bit here, and that is work. So, in general, if an object moves in a straight line with position function s of t, the force of the object is denoted with the letter F. F equals ma. Right, mass times acceleration. So m we keep the same, but a, acceleration, if we remember from Calc 1, you can write that in terms of the position function, and it's the second derivative. So we write d squared s over dt squared. So force is mass times the second derivative of position. When acceleration is constant, the force is also constant. Okay, so when acceleration is constant, the force is also constant, right? Because mass is constant as well, right? The mass isn't going to change by applying force to it. And the work done is defined as W equals F times D. And this is where W represents work. F is, of course, the force. And D is the distance the object moves. Okay. So we can find work by just taking force times distance, right? So the amount of force it takes times however far you want it to go. But this then begs the question, what if the force was variable, right? What if the amount of force that it takes to do something changes as the object moves, right? So if we're talking just in a hypothetical scenario, right, if I'm moving a box, right, across a surface, it's going to take so much work to do it, right? If I'm sliding it across the grass or the sidewalk, some smooth surface where it doesn't have a lot of friction, it just pushes. But then if I take it to the beach and I'm trying to push it across the sand, there's going to be a lot more resistance there. So what if the force changes, right? What if it changes as we're going through this process of applying work to it? So if an object moves along the x-axis in the positive direction from A to B, and at each point a force acts on the object, where f of x, that force function, is continuous, then the work can be found using the integral from A to B of f of x dx. Okay, a nice, simple, concise, just an integral. So if we can identify the function that represents the force, we can find the amount of work being done over the distance from A to B. So let's look at an example. When a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? So we have work is the integral from 1 to 3 of x squared plus 2x dx. Antiderivative, get x cubed over 3 plus x squared from 1 to 3. And that is 50 over 3. You could write it as a decimal as well, but this is an exact answer. The units on this, by the way, would be foot-pounds. Okay, so you don't need to worry too much about the units in here, because this obviously isn't a physics or engineering class. Focus more on the integration aspect of it, but that's what we get, so just an integral. And then we have a law that applies to this concept, and it's very much related. So it's Hooke's law. So Hooke's law states that the force required to maintain a spring stretched x units beyond its natural length is proportional to x. So we have f of x equals k times x, where k is a positive constant called the spring constant. Okay, so again, Hooke's law tells us that the force required to maintain a spring stretched x units beyond its natural length is proportional to x, that number of units. So in other words, right, I have a spring and it has its natural length. So think of it like with a slinky, maybe, if you've played with a slinky. If I want to stretch this spring out, I'm going to have to apply force to it, right? Apply work to it. So if I stretch it out, a certain amount, it's going to cause an increase in, right, the amount of force that is required, right, as the distance increases, right, x. If I stretch it really far out, it's going to take a lot more work, a lot more force to keep it stretched out that far. Okay, so that's all this is saying, is the more you stretch it, the more force that's required to keep it stretched that way. Okay? And it turns out, thanks to Hooke, that we found that it's actually proportional. So the amount of force that you need is directly proportional to the length that you're stretching it. Okay? So let's look at an example of this, how this is utilized. So a force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to a length of 15 centimeters. How much work is done in stretching the spring from 15 centimeters to 18 centimeters? Okay, so we're going to start off with a little bit of explanation here. So let's kind of talk about what we know. So when stretching from 10 centimeters to 15 centimeters, it is stretched 5 centimeters, right? 5 centimeters above its normal length. One thing I do need to mention, though, in the context of this formula, so Hooke's law is in terms of meters, not centimeters. So we're going to actually convert these centimeters into meters, and it's 0.05 meters. Okay, so just bear that in mind. You'll need to do that. So when we're trying to look at the force was 40 newtons, right, to move it that far. So we have F of 0.05, right? That's the x value, is 0.05. The force required is 40. So by Hooke's law, we know F of 0.05. We know that that force is directly proportional. So we can go ahead and say that F of 0.05 is 0.05 times K, and we know that that's 40. Okay, so, right, that's K times X. X is 0.05, and we know that the force is 40. We can use this to solve for K, and then once we have K, we can use it to find the force for any other length. So, solve this for K, so divide both sides by 0.05, so 40 divided by 0.05, that's actually going to be 40 times 20, which is 800. So K equals 800. Thus, if K is 800, the general formula for that force, F of x, is going to be 800x. Okay, so that's going to be very useful to us, because now I can determine force for any distance. Okay? But look back at what the question is asking. Okay, so a force of 40 newtons is required to stretch it from 10 to 15 centimeters, it's asking how much work is done in stretching it from 15 to 18. Okay, so in stretching it from 15 to 18. Now we're asking for, keyword here, work, not for force. So just have to be mindful of that. So the work done to stretch the spring from 15 centimeters to 18 centimeters is what we're going to find right now. So remember, just as a side note here, the amount of work done is the integral from a to b of f of x dx. So for this one, we have f of x, and we can get a and b. So work is integral of 800x dx. And the lower bound, we're starting at 15 centimeters, but we're putting that in context. So we're not looking at the 15 by itself, we're looking at how far above its natural length has it stretched. Its natural length is 10 centimeters, so the amount above that at 15 is what we saw earlier, is that 0.05. So our lower bound is going to be 0.05. And it's getting stretched from that to 18 centimeters. And 18 centimeters is 8 centimeters above its natural length. So converting that into meters, we get 0.08 for our upper bound. Take the antiderivative, that's 400x squared, evaluated from 0.05 to 0.08, which then we find gives us 1.56, and the units on this are actually joules. Alright, so we're combining pretty much all of these concepts from this section in this problem. So the idea of applying Hooke's law to find k, that spring constant. Okay, once you get the function for force, you can use it in the function for work, and then identifying the bounds in terms of the distance past its natural length, right? How much extra are you stretching it? Okay, and then putting it in the units for meters instead of centimeters.